Thanks a ton for joining. This is the second episode of AI, the podcast. So tonight I'm going to be joined by Andrey Seryakov, who is a dear friend of mine. I've known him for ages, really. He's one of the most brilliant people I think I know. He's a physicist at CERN. So tonight we're going to talk about Large Hadron Collider. We're going to talk about the future circular collider, as well as the theory of everything and why everybody should care about this, no matter how far you are from physics right now. So, and we're going to talk about these things in really, really simple terms and concepts, I think, because if you cannot explain this to 6-year-olds, that means that you cannot really understand this. Is that right? I think you know whose quote is that. So, a few words about how me and Andrew met. It was actually by the time when I was owning my first business ever. It was a key space hacker dojo in a way in St. Petersburg back in 2014 or 2015. His first ever lecture at my lectorium was called Quark gluon bouillon, or why should every housewife should care about the Large Hadron Collider. Is that right, Andrew? So yeah, thanks, buddy.
Something like that, yeah.
Thanks a ton for joining me. I really appreciate this. So yeah, first thing is that could you please go ahead and introduce yourself, because there are so many things about you that I cannot really recall.
So I'm a scientist from St. Petersburg, and I'm working in a university, and I'm also working at CERN. So in my scientific life, I'm doing heavy ion collisions. This is why it's soup of quarks and gluons, which I was talking about. It was one of my first public lectures. It was like 6 years ago, something like that. And yeah, now I have a blog about particle physics, and I'm a member of two international scientific collaborations. One of them is called SHINE. It's at CERN. It's doing exactly heavy ion physics and also a bit of neutrino and cosmic ray physics. And I also take part in building a new experiment in Russia. We also are building a new collider here, much smaller than Large Hadron Collider. It's called NICA. And I'm participating in the second collaboration there. It's called MPD, which also aims to study this quark gluon soup. And I'm also an outreach science communicator, and giving a lot of lectures, mostly in Russia. And I'm an outreach coordinator at CERN of the SHINE experiment and visit coordinator there. And I also guide to the Large Hadron Collider. So if you, by chance, going to visit CERN and want to go underground, you may contact me, and we'll think how we can make it. Yeah, that's probably if I want to introduce myself and short.
Thank you, Andrey, because I could really never recall all the things you are, really. So look, the first thing I have for you is that a lot of the scientists I know, a lot of the physicists I know, right, do get their calling in their life, like the path they should be in really, really early on, compared to all the different business people, compared to my experience, how I got into the business. It was more of the coincidence in a way. But then what actually inspired you to do this thing and to dedicate your life to doing this thing in a way?
I would say books which I read, yeah. So I started reading fantasy and science fiction when I was 8 or even 7 years old. So, and then you're becoming older and older, and you're growing, and you're reading all this literature, and I don't know, at the age of something like 11, 10, you start to understand that all these beautiful technologies you're reading there, I don't know, traveling through space and time, or I don't know, visiting other galaxies, it's building space stations. It's so far away from our current state of technology.
This is really fascinating. But look, the thing is that what actually got you to the Large Hadron Collider in the first place? Could you talk to me a little bit more about that? Because I was really fascinated about hundreds of scientists working on the same project, full speed all the time, right? And then how it actually happened.
Even thousands.
Yeah.
For me, it was pretty simple. So I got to physics department of St. Petersburg State University, and then after the second year, you choose where you're going to write your diploma thesis or where you're going to write a bachelor thesis. So I chose theoretical department, which is devoted to high energy physics. But I didn't like really theory this time, but that was the strongest department in the faculty. So I went there and I found an experimental laboratory there, the only one, which works at CERN. So I was doing experimental physics at the theoretical department. And we as a laboratory of ultra-high energy physics, we take part in several different international collaborations, including Alice collaboration at the LHC. So during my master program, so I finished my bachelor's and I went to my master. In Russia, it's typical not to. So we used to stay with inside the same university for bachelor and master, and even for PhD after that. So somehow it's a different system than in the western part of the world. So during my master thesis, I went to CERN first time for the summer program for 2 months and was working there. And after that, I just going there several times per year. Yeah, and spent there like 3 months per year.
Why do you think that was it? I mean, of course, obviously, that was the largest experiment of the humankind ever, right? It was the largest machine ever built right now. Yep. Not before the FCC, which we'll talk about in a second. But then...
Yeah. So what...
Go ahead.
Yeah, could you tell the question? Yeah.
Sure. So the thing is that
question.
About the Large Hadron Collider is that the largest discovery of that was the boson-Higgs, for sure.
Yeah, Higgs
which was
boson,
granted, which granted, it was like 2013, the Nobel Prize. But the two scientists that actually predicted the boson-Higgs ever existing 60 years prior to that, is that right?
Yeah, something like that, 50 years
that
ago.
Was crazy.
Like that, in the middle of 60s.
Yep. So for me, like Large Hadron Colliders, like collisions of the elementary particles, was almost like traveling back in time in a way, because you could actually discover the particles which don't ever exist in their natural state anymore.
Important for understanding how mass is originated, mass of all elementary particles. So it means that we like thinking right about that.
Why did they refer to the Higgs boson as a God's particle?
Yeah, come on, it wasn't God particle, it was goddamn particle because it was hard to find, and that was just a quote from one of the physicists, and journalists so like it. It's the same about all these black holes at the LHC. So journalists just like such names, and they starting to copy it and reproduce it. So there is no like deep meaning in that.
Mm-hmm. So it's more about the marketing, is that right? But then again, look, Andrea, a ton of people do say that our universe would never be the same. It was such a small intervention in a way, because at the time of the Big Bang, the matter should be equal to the antimatter. They should like destroy themselves. Is that right?
Yeah.
So and then in collision, like with all of the, let's say, cosmologists, we do understand that there's a lot of the dark matter. So is one of the experience.
That's a different question.
Yep. Go ahead. Elaborate, please.
Yeah, so if you're talking about matter-antimatter symmetries, it's not really connected with dark matter. So we believe that in the first moments after the Big Bang, the universe was filled with pure energy. So there are no matter yet, and then matter and we cannot call it light. Yeah, just energy. We don't know in which way it was there, because energy from Einstein equation, E equal mc squared. This means that energy and mass is the same. When we collide, so Hawking said that LHC is the closest technology we have to the time machine, and he meant that when we are colliding anything at the LHC, we are somehow reproducing energy density which existed at the first moments after the Big Bang. So LHC, this is the only way how we can look there and study how matter behaves and how universe behaves when you have so large energy densities. So, for example, LHC in the current state reproduce conditions which existed in our universe first second at the very first microsecond after the Big Bang. And if we reproduce it, so we also collide particles there, the LHC, so we create a pure energy from this collision. There is a huge kinetic energy, and we create matter from it. So, and we see that we reproduce exactly the same number. We produce exactly the same number of matter particles and antimatter particles. So it means that already at the first microsecond of our universe life, symmetry between matter and antimatter, it already was there. So so it wasn't broken. It's also like restored already. So if it's break at one point, it was broken before first microsecond, and the only way to go there is to build the larger machine. So to reach highest energy, reaching the highest energy. It's the same as looking farther, like closer to the moment of the Big Bang. And to understand where is this symmetry, when this symmetry breaks, at which energy density.
Look, one of the most famous quotes I think of Albert Einstein was like, the more I study science, the more I believe in God. What do you think about this one?
Oh, come on, that's a different story, and I for me it's opposite. But there is such.
That was not a conventional personal God, of course, right? It's something that he always believed, that the question of whether or not there was existence of God was something that was just too big to our limited minds. Like, what do you think about this?
I mean, first of all, we are monkeys, yeah? For once. And we were not apes, so we were not created to study the universe. I mean, nobody created us in evolution. So
I agree.
But I don't believe in God, I mean.
Mm-hmm. No, not a conventional God, a personal God for sure, but then something that actually the creator in a way, whether or not
I don't think
this thing exists.
No.
So you're like purely like God agnostic.
For me, it's like philosophy is as in mathematics. If you have a formula, I don't know, a law, a mathematical law which describes something,
right?
You're trying to make such law that it would be the simplest as possible. Preliminary, this is a concept, yes, so it's not proved. It will be built in the same place. We will need 20 years to build it. So it will be 100 kilometers long, and it will. So but we don't really care about length as physicists. We care about energy there. So if collision energy at the Large Hadron Collider is 14 TeV, so compared to TeV is so this is tera electron volts. So I would compare it with mass of proton. Proton mass is 1 GeV. So 1 TeV is 1,000 times higher. So and proton collisions at the LHC, they have collision energy 14 TeV, and the future circular collider we have 100 TeV. So it's roughly, I don't know, 7 times higher.
They're gonna spend like $22 billion on this thing alone.
Yeah, not much, I would say.
I don't really think that's a ton of money, but we could spend this money elsewhere. Why do you think it's important to do this thing?
Yeah,
and
actually,
then the most important thing for me is like Of course, why do investors put all this money? But then, look, what is the most important discovery? First off, they want to make out of the FCC, right? But also, what is the outcome, the consequences for all the people in their day-to-day life, potentially?
Described by a completely different theory, which called general relativity theory from Einstein. And they're already separate ones. It's really hard to merge them together. So we need to have a theory of everything. If you really want to understand the universe, we need to have a theory which describes all four forces and also dark matter and dark energy and everything you see around. So the one way to do
Andrew,
it is to
first
find
off, for all of our listeners, can you talk to me a little bit more about what dark energy is? Because we know it's everywhere, right?
Okay.
It's like sliding through our bodies as we speak. Like, what is the dark energy exactly?
No, that's a different thing. So dark energy is some kind of like feature of our space and time. So this is not a dark matter which goes through all our bodies and all. So yeah, so there is matter,
right?
Which we all made of.
Yep.
And
there's
there are
antimatter.
And this is not many antimatter in the universe really. It's really small. Really care for if you're talking about universe, about antimatter now. So this is like ordinary matter is around 5% of all energy in the universe. Then I have dark matter, which we see by observing galaxies, large scale structures of the universe and all this stuff. And we have there are 5 times more dark matter than ordinary matter. And it's based, rotation of the galaxy based just simple Newton laws from school. So nothing really sophisticated there. And we can, based on the mass distribution, we calculate rotation. And we see that it rotates much faster than we would expect. It means that there is some hidden mass there. And this is one thing, and we understand there is a lot of such mass, especially in the hull of every galaxy. That was first observable, where we understand that something is going on which we don't understand. Then there is a large, scale picture of the universe. If you may see such picture somewhere right now. It looks like a web, a huge web of galaxy clusters. So this formation of this web of galaxy clusters can be possible only if there are much more particles in the universe than we see. Than matter particles. So like 5 times, exactly 5 times more. So to form universe in the way we see it now through telescopes, during 14 billion years. As the life of our current universe, we need additional mass, a lot of additional mass, which doesn't interact electromagnetically too. So that's a long story to explain it, but that's now observable. And there are also bullet clusters. If you Google, it's really written like that, bullet clusters, and this is collision of 2 galaxy clusters. And we see that there are 2 components which we also can measure, 2 components of mass, and one component is you have collision of two galaxy clusters, and they start to interact between each other. And this is only part of their mass, but most part of its mass goes through without interaction, and it is invisible for us. And we see it by gravitational lensing. That's another effect. So we can see curvature of space and time around this matter there, which is invisible. And we understand that there are a lot of matter there, but it is invisible, so we can conclude that there is dark matter, invisible matter. Yeah, that's about dark matter.
What is the most important discovery they're planning on doing on the future circular collider? And then, second of all, why do we need to spend this much money on this? And when is it going to be built, though?
So we don't know what we can discover there because we don't know what we are looking for. Exactly. So the difference between Higgs boson discovery and all this new physics discovery, which which we aiming now, is that Higgs boson was discovered, and now we don't know where to exactly look for it. So it may happen that we will discover nothing there. Yeah. Of course, it will be great to discover like theory of everything, graviton. I mean, I'm trying to be realistic, and I'm a scientist, so I want to be like as much as. I want to present you how we think about it. Yeah. So we may hope that we will discover everything there, but there is a chance. So
can you elaborate on everything, please? That would be interesting.
I mean, there are many questions which you discussed before, like matter-antimatter symmetry. There is this dark matter, dark energy, and maybe after building future circular collider, we will understand everything. There is very small chance of that.
It's only like 4 times larger than the Large Hadron Collider. It's not that big of a deal, is that right?
Right. But we don't know where answers are. So the beautiful thing about
do we know the questions though? Because you cannot really get a good answer without getting a very good question though, right there. You know?
I mean, it depends what you call a question. Yeah. So like in general, we have questions. Yeah, we want to understand.
What is the most important questions? What the universe is, what's the basic law of the universe, is that right?
So like the discovery of dark matter particle would be I don't know, a breakthrough.
Like, can you talk to me a little bit about like why the discovery of the dark particle is going to be a breakthrough for everybody, including like a housewife, person really, really far from the physics, like.
That's a different thing. I don't know. I mean, there are many reasons why to build future collider without any discovery, even without any discovery, because you have a lot of like side discoveries, as web, for example. Yeah. So World Wide Web was built at CERN. Created at CERN 30 years ago. And it was built because scientists from
reasons, that right? And then pornography.
Yeah,
happened.
I mean because we wanted to build a LHC this time, and for that we need a collaboration of like tens of thousands people from around the globe, and we needed a web to communicate between each other. We need web pages and all this, and now we use them to communicate like. After that, it became open and everybody is using it now. So there will be many such side effects because we are pushing our technology further. So this is like the cutting edge of the human technology, and there is no way as we can move through it without creating new things, because nobody ever think like that before. Yeah.
What are the up-and-coming technologies that we can expect from the like CERN and the LHCs, though? Can you talk to me a little bit more about that?
There is a new technology on X-ray imaging, like colorful X-ray imaging. It's based on MIDI-PIX pixels, which is detectors which were used for particle physics. So this is pixel detectors to trace particles at the Large Hadron Collider, but then people realized that they can use it for imaging and for X-ray imaging. And for example, they build X-ray scans at CERN now, test ones, so which have colorful images, and the also beautiful thing about them that they can make image even without with some metal plates inserting in our body. Yeah. For example, there are also some technologies for art. Like 2 years ago, CERN announced that they started to produce some like meter-long small electron accelerators for art testing. For example, to understand what chemical compounds of different art pictures or anything. I don't know. I'm not an expert there. So there are many small discoveries now. Nothing like such big as the World Wide Web, but there are many small ones.
So, can I ask you about this one? So, I already referred to this Einstein's quote, right? That human brains like way too limited to the understanding of the most important question, the problem with the universe, like absolute one. So, I was just wondering whether or not you're using some sort of AI technology, some machine learning to, let's say, analyze
A
like
lot of
billions of like photographs taken, Large Hadron Colliders on a daily basis. Like,
Yeah. So this is a really hot topic for us. So we are using machine learning a lot. Yeah. Even I do that. Yeah. On my not my daily basis, but I'm doing machine learning from time to time. So because we are on the cutting edge, we do everything which can serve for our needs. So yes, image recognition, for example. Yeah. So all this stuff or yeah. So that's the first thing which came to our mind. So there are also some like event selection. It's called event selection, event criteria selection. Yeah, because then you have collision of and many particles are like created there. You want to understand is it an interesting event? Is it a good quality event? So you're training. They use different approaches. Usually that's three.
Andrew, sorry to interrupt you, but the interesting events do happen like once in 100 billion times. Is that right?
Depends on your aim. Yeah, depends what physics you want to study there. For example, for my physical quark-gluon plasma, most of events, I don't know, like 5% of events are interesting ones. But for some rare physics as Higgs hunt, yeah, if you're looking for some rare cases, then it can be one event per million, something like that. Yeah, I mean, even is a collision. Yeah. So I don't know. Machine learning is everywhere. At CERN too. Each experiment using it, each facility using a lot, and even many physicists using it. The only drawback from it that if we insert machine learning in our physics picture, not in detector picture, there is no problem if we insert a neural net in our detector for that data reconstruction, I don't know, for data selection, then it's okay. But if we use machine learning to understand physics beyond these processes, then it's a problem because usually all these neural nets, they are black boxes. So they give us some answers, but they don't explain why this happens. So we cannot rely on them. We can only use them to guide our eyes to guide us to potential place where discovery can happen, but we can't 100% rely on them because our ultimate goal is to understand. Neural nets do not explain anything.
From what we're talking about right here tonight, I mean, I do feel like the only goal of physics, like to understand like how the universe was created, like how is it functioning, how is it possible? Is that right?
I mean, not just created, but how it's functioning now and where are we going? So everything.
Is God the real thing, right? So that's why we're kind of, in a way.
I don't think we need one.
Yeah, I don't think either, but then in a way, it really looks like this is the question that everybody's trying to answer to. I mean, not the conventional personal God,
this
for
is
sure.
Simple.
But
I would say this is a simple answer, and we are not looking for simple answer. Yeah, we are looking for understanding, and that means that our universe is a very complex.
Do you have the question deep enough to get an answer, that we're really?
I mean, I do. I don't know.
You do?
I think there's all these questions that are very deep.
Don't you think you're really too limited by your human consciousness?
I am 100% limited, and I'm understanding that, and that's our that's a great insight of humanity, that we understand our limitless, like not limitless, like that's limited, exactly, and that we are trying to build our understanding of the universe based on math, not based on our brain and our feelings. So this is how science works. At least this is how we want it's working.
Agree, but then math is not everything, though. Do you know why they didn't include the math into the Nobel Prize ever?
Oh, come on, that's yeah, because Nobel didn't think math as a science discipline. But no, that's another thing, that Nobel is obsolete.
I know, but then my grandmother told me that his wife actually ran away with another math scientist.
Oh, that's also can be true, but that's I don't know. I'm not a fan of history things, so I know really little about history of physics and all this stuff. But the thing that Nobel Prize is pretty obsolete now. Yeah, you know, all these major discoveries of 21st century were made by, in experimental physics, were made by thousands of people. Like gravitational waves, all this Higgs boson, or like black. You may heard about this black hole picture. They were made by thousands of people. You cannot like choose one of them, a leader of them, and give them, I don't know what is the Nobel Prize. So you need because it's a collaborative international effort. Yeah. So this is why like Nobel Prize is something which is 100 years old, more than 100 years old. I don't remember when it was founded, but anyway, now science works completely in a different way, and yeah, I don't know what to do with that. Nobel Prize is a good thing in terms of scientific visibility, but I don't think we need to aim for that.
But then look, Andrey, how exactly do those collaborations between the scientists work? I mean, there are like hundreds, if not thousands of people involved in every single one of those experiments, right? So how exactly do you share the knowledge between yourselves, and then like how do you come to conclusions? Yep, that was a really interesting one for me.
This is a very horizontal structure, yeah. It's very horizontal because, for example, these large experiments at LHC, largest of them have I don't know, around 5,000 physicists inside and engineers, and they somehow clustered by small groups. For example, my group consists of 20 people in St. Petersburg. So it means that there are hundreds of such groups around the globe, and they're all parts of the same scientific collaboration. They need to communicate, and that's a really tough task. Yeah, they're not sitting in the same building. They're sitting in the different countries. So you need to build such structure. So they also cluster together to answer different questions, to build different subsystem of detector. So there is hierarchy of different tasks in such collaboration.
So you do distribute the task between yourselves, is that right?
Yeah, of course. You specialize in different things. You're doing different stuff, and you have a lot of you do a lot of video on your daily base. So, I mean, all humanity started to do it last year, but we were doing it for last 20 years as scientists. And there's other things. They called collaboration meetings or collaboration weeks. So we have close conferences.
Look, it's been a year almost since the beginning of the pandemic, right? It's been exactly a year. Oh my God, a year and 1 day since I ever experienced the lockdown back when I was living in California back then. So what was the most important thing you discovered about yourself during this 12 months, you'd say?
I don't think that I learned a lot, but I decided to try a lot of things. Yeah, that's about my personal life. So I started to build relations with my partner in a way as I wanted like years before, and I planned that and all this stuff, but I didn't start. But then that's probably coincidence. I don't know, but somehow. I don't know, because we started to do that at the end of January and pandemic struck at the end of February. So that's maybe a coincidence, maybe not, but it somehow accelerated everything. Yeah, so I'm pretty happy about that. And now I live according to my, I don't know, how I think it should work, how I believe it will be honest and like right to live my life. And that's a great thing about this last year and this year too.
Yeah, that's true. I actually learned today. I've learned the definition of insanity is like doing the same thing over and over again, expecting the different outcome out of every single one of those. So, I actually thought about this a lot today. You know, like if I keep doing the same thing over and over again, like, can I really expect different outcome? I don't really think so. So, because that's crazy in a way. So yeah, I decided to do a lot of things about my personal life, like today, really.
Yeah, so I would say that this year it will be a beautiful one because we would expect many. So because I think that all people on the globe, they have some kind of an insight about their life, and they decide to change a lot of things around. So I would say that next several years would be filled with a lot of new ideas and new projects. They will be very interesting.
Do you expect it to go up like this, like a V, or like a U shape? What do you think? For scientific community, though.
I don't know. It's hard to guess. I don't have a mathematical based model yet. Oh yeah, yeah.
Yeah, that's for sure. All right, buddy. That was a pleasure to have you coming over today.
Yeah, it was a pleasure for me.
All right,
Yeah.
Andrew, thanks a ton for coming over. Here we go. Thanks everybody for joining us tonight. And then, yeah, if you have any questions for Andrew or like, please leave it down below. We'll try to comment every single one of them. And yeah, pleasure having you all. Bye. Take care.
Bye.